So we've moved on to the second part of our angular momentum problem, and the second part says that using the equation that we created in the last part, what is the final angular velocity that the woman had? So her torso's radius is 0.2 meters, and that would just be the radius of our cylinder, and her arms are 1.7 meters long, so that would be the length of the rod that we had in the first part. So we have this huge equation written out here, and it's actually the equation that we had at the end of that last part that we had flushed out. It's so long, but it is our equation that puts together our rotational angular momentum of our rod or her arms, and then the rotational angular momentum of her body without her arms in the initial state altogether, both with the same initial angular velocity, and then in our final state, just the rotational angular momentum of her body as a cylinder altogether, including her arms, and then times the final angular velocity, which is what we are looking for in this part. So thanks to the fact that we had to flesh this all out in the last part, all we have to do is plug in all of our numbers into these multiple variables and then calculate for our final angular velocity. And with that, we can just start. So we have 1/12 times the mass of her arms, which is 7, and then 7 kilograms, and then times the angular momentum, the length of her arms, the same variable, angular momentum, of course, represented by the capital L, but the length of her arms squared, which we were given as 1.7 meters long, and that will be squared. And then this is times the initial angular velocity, which was just 1 rotation per second, so this is just times 1. And then we are going to add the angular momentum of her body, and this is minus her arms, which is important for the mass that we're going to write down. So we have 1/2 as a cylinder times the mass of her body, so the total body mass that she has is 60, and then minus the mass of her arms, which is 7 kilograms, so we get 53 kilograms. And then this is multiplied by the radius of her body squared. So we said that her torso's radius is 0.2 meters, and we can just approximate this for her entire body, which is not accurate, but you know, we're just gonna go with it. So we have that, and then this will all be times 1 once again, because we have an angular velocity of 1 rotation per second. And then we have to set this equal to, it's so long we can't fit it along this stretch. We have this set equal to the cylinder that we ended with, which was her body, but her total body mass this time of 60 kilograms. So we have 1/2 times the mass of her body total, which is 60, and then times the radius of her body squared, which is once again, despite bringing her arms in, it is once again 0.2 meters all the way down, so 0.2 squared. And then what we are solving for is our final angular velocity. So what we're going to do first is we're just going to calculate this huge stretch of our initial state. So we'll multiply these numbers and then add the multiplication of these numbers, and that number that we are going to get is 2.746, and the unit for angular momentum is kilograms times meters squared per second, which is complicated. But anyway, we can set this equal to all of this multiplied together, which ends up being 1.2 times our final angular velocity. So all we have to do is divide by 1.2 on both sides, and what we end up with for our final angular velocity is 2.3 rotations per second. So just the woman having her arms out, spinning around, she only had 1 rotation per second for her initial angular velocity. And the moment she brings them in fully close to her body, she gains 1.3 rotations per second. So that is quite a bit faster than she was before. But from this huge, long equation, we have this simple answer for our final angular velocity. And with that, this part and our problem is done.